think my tongue got a little twisted at the end of that last section. Let's go through this slide again. So far we focused on those aspects for a spontaneous reaction where delta G must be negative. But another measure of reaction spontaneity is the equilibrium constant. For a reaction to be spontaneous, K must be greater than 1. In other words, the products of the reaction are favored over the reactants. The relationship between this delta G and the equilibrium constant can be found by stating this general equation. Delta G equals the free energy of formation plus R times T times the log of Q. Now, at equilibrium, delta G, this equals 0, and this right here equals K. So 0 equals the Gibbs free energy of formation plus RT ln K, or delta G equals minus RT ln K. So this relationship between the Gibbs free energy and the equilibrium value holds for all equilibrium constants that we've discussed in this course. We've talked about their precipitation, the activation, the water, the acid, base, formations, the dissociations, the solubility. All these different equilibriums have this type of relationship. So now we can relate the standard free energy change of a reaction to the extent of a reaction. In other words, as with enthalpy, free energy changes for reactions are additive. If you've got two different reactions as a part of reaction 3, this Gibbs free energy for this reaction just equals the initial states between this one plus this one. Also keep in mind that if a reaction is reversed, then the sign in delta G is also reversed. If a reaction is multiplied by a factor n, then delta G is multiplied by that factor n. So what we're looking at here is the Gibbs free energy versus the reaction progress for standard free energy changes. Here you have a negative one. So you are going from reactants to products, and the overall delta G is here, where you overcome, where it goes down this low and this is right here is your where your equilibrium constant is. Likewise, if you go from reactants to products and have to put energy in for a non-spontaneous one, it would follow a path like this. Likewise, if you have the same delta G, forward and reverse, it would look like this. So non-equilibrium systems will proceed spontaneously in whatever direction is necessary to minimize free energy and to establish that equilibrium. And that's the end of this chapter. We're going to continue directly on with chapter 12, talking about kinetics. And first of all, we'll talk about the rate on which these certain reactions are taking place, factors that are going to affect those, the different rate laws, and how we can utilize integrated rate laws. But you don't have to worry. You're not going to have to worry about, you're not going to have to do some calculus on this. That's not going to enter into it. The collision theory, reaction mechanisms, and the effect of catalysis. So, chemical reactions occur at different rates. Some reactions are fast, other reactions are slow. Chemists study these in order to control these, because otherwise what happens? It's just a big boom, right? So, the study of reaction rates is known as kinetics. The rate of reaction is the change in the amount of reactant or product per unit time. It's often convenient to express it in terms of concentration. And then what we're going to end up with then is a rate expression, a mathematical representation of the rate of reaction. Reaction rates are always positive quantities. Concentrations are most often expressed in molarity. In other words, the number of moles per unit volume. Rate expressions can be written in terms of reactant or product concentration. So, for example, here you have hydrogen peroxide as a water going to form water and oxygen. And to write the rate of hydrogen, this should be H2O2 here. Okay, decomposition. This is a misprint here. It becomes this material right here, minus the formation of this, minus the initial amount of this over the change in time. So the final concentration minus the initial concentration divided by the time between the initial and final point gives you the rate of this decomposition. Likewise, the rate of formation of the water there is going to be the amount of water you have initially, probably 0, minus, the final amount minus what you had. This is the one that would be 0 here, okay? And then times divided by the time interval over this formation. And a similar equation for this one right here. So if you were to look at the rate of decomposition here, you have it going from time 0 to 6 hours, it drops down in half, right? So this is the change in concentration divided by this time to give you this rate of decomposition. Likewise, here's another 6-hour interval. Here it drops in half again. But this is 0.25 times that. And so the rate of decomposition between those 2 points is this. And so you can see that the rate of decomposition is going to change with time. And that is to be expected. Okay? So the average reaction rate is the rate at which a reaction proceeds over a time period. It's calculated using the concentrations at the beginning and the end of the time period, just like we did in the preceding slide. Instantaneous reaction rate is the rate at which a reaction is proceeding at a specific time and or concentration. And what you do is you use a graph of concentration versus time and a slope of a straight line tangent to a curve at a specific time to get that instantaneous reaction rate, or by determining the average rate over a very short period of time. The initial reaction rate, the instantaneous reaction rate, is at time 0. So here you can see that this is your initial point, and here what you're doing is an instantaneous value here. Okay, so the slope right here is the change in this with time at this particular point. The overall change is from this final point here minus this initial point here. Okay, and so what you are doing is you are looking at this particular triangle here to get the these values for x, these values for y, and these values for x. So this would be your time final, and this would be your concentration final. This would be your time initial, and this would be your concentration initial. So the smaller this interval becomes, the more closer you are to an instantaneous rate. So the rate of reaction may be expressed in terms of the change in concentration of any reactant or any product. Stoichiometric factors derived from a balanced equation may be used to relate reaction rates. And at this right here, you can see that you've got initially ammonia, right? And it's decreasing, and you are forming from that nitrogen gas and hydrogen gas. And you're looking at an instantaneous rate here, an instantaneous rate here, and an instantaneous rate here. Okay? So this graph shows the change in concentration of reactants and products during the reaction. And they're related by those exact equations that you have, and you can have the slope values for at different points here and here that you are looking at. Now, the chemical nature of reactants. What I'd like you to do is I'd like you to pause and click on this U-tube right here, where you see the group of alkali metals react at a faster rate. And you'll see that as it goes down through lithium to sodium and beyond, you'll see just how much more rapidly those are going to react when they get into water. As a matter of fact, the final one is just going to almost explode up into your face. Fortunately, we didn't have to do that in our lab because we didn't have a hood. So also, another factor that affects reaction rate is the state or subdivision of the reactants. In other words, if you increase the surface area, you're going to increase the rate of reaction. A lump of something is not going to react nearly as quickly as if you've got small little iron filings. For this example right here, you've got an iron powder here, and it's reacting very rapidly in dilute hydrochloric acid and producing all these little bubbles. If you've got just a nail down into that, it's going to react with that acid as well, but it's going to be much, much, much slower. Temperature also affects the rate of reaction. Reaction rates normally increase with temperature. The usual rate of a reaction, usually for every 10 degrees increase, and that's 10 degrees Celsius or 10 degrees Kelvin, you get a doubling in terms of the rate of reaction. That's a good rule of thumb for many, many reactants, assuming that the reaction is starting already. If there's no reaction, then of course it's nothing to increase. The concentration of the reactants also affects it. In other words, if you've got a higher amount in that solution of a given reactant, that's going to push it forwards, and the presence of a catalyst. Let's talk about rate and collision. The reason why something at a higher concentration reacts more readily is because it's more likely to run into another molecule. So these chemical reactions occur as a result of collisions between these different reactant molecules. The higher the concentration, the more likely they are to collide, and the faster the reaction will proceed. And again, there's another YouTube video here that you can watch, and you can see that how rapid it goes. But we saw things like this when we added more and more of sodium bicarbonate to an acid solution. As reactants get consumed, the collisions happen less frequently, and the reaction rate decreases. That's why you get the overall fast upsurge and then a slowing down, right? So the reaction rate is directly related to reaction concentration. In other words, for this one right here, reaction rate law for this reaction is the rate equals K times the concentration of N2O5. Only the reactants appear in a rate law, okay? Only the reactants. So if you only have one substance over here, that's the only one that's going to be in there. And K is the rate constant for the reaction. This is not the Boltzmann constant. This is an individual constant that is determined and calculated specific to this particular equation. The rate law is used to calculate instantaneous rate or initial rate of reaction for a specific reaction concentration. Some reactions are more complex. The rate constant is specific for a particular reaction at a particular temperature. It's independent of reactant concentration, and it must be determined experimentally. It is not a constant. So the experiments must be done to determine these, and you just can't balance a chemical reaction. For a reaction with a single reactant, rate is Ka to the M, which is the order of the reaction, or the order of the reaction. And this order must be determined experimentally, not from a chemical balance equation. This is not the same as the coefficient in front of A, okay? Reaction orders are usually positive integers. They can be 0, 1, or 2, but can also be a fraction or a negative number. Most reactions involve more than one reactant, unless it's a decomposition reaction, and therefore the rate would be each one of these raised to their individual order. So M is the order with respect to A, N is the order with respect to B, and the overall order is m plus n.